Here's a diagram of the Earth-Moon system. Now, can you see what's wrong with this diagram? Yeah, the distance between the two is not scaled properly to their sizes. So the distance between the Earth and the Moon is about 60 times the radius of the Earth. Now here I've called it d instead of r because I don't want to mislead you. It turns out the Moon does not orbit in a circular path with the center of the Earth as the center of that orbit. So if we label the distance between the Earth and the Moon as d, let's see if we can get an idea where the center of mass of the Earth-Moon system is. Yeah, if the Earth and the Moon were of equal mass, then the center of mass of the system would be exactly halfway between the two. Because the Earth is enough larger in mass, then the center of mass of the system is maybe right there. X marks the spot. So maybe we can say the distance from the center of the Earth to the center of the mass is some value x. So both the Moon and the Earth are simultaneously orbiting about the center of mass. So you can picture it as if there's some axis of rotation represented by this gray line, and if you were to take the system and spin it about that axis, then the Earth is orbiting in a smaller circular path, and the Moon is orbiting in a larger circular path. And so they orbit the common center of mass of the system. By the way, the Moon is large enough, it compares fairly well with some other dwarf planets in our solar system. Let me remind you of some of our dwarf planets: Pluto, Eris, Makemake, Haumea, Ceres, and quite a few more. So if we change the qualifier for a planet to include Pluto, then we'd have to also include Aries, Makemake, Haumea, Ceres, and probably our Moon. So it's fair to say that the Earth-Moon system is very nearly a binary planet. Let's imagine a binary star system. There are plenty of those in our universe and in our galaxy. So what if we had one star whose mass, capital M, is greater than its binary partner, whose mass is lowercase m, and they're separated by a distance that we call d, measured from center to center. The center of mass is somewhere here, x. So the distance to the smaller planet is a distance of d minus x. How could we apply Newton's law in this case to find the period of orbit? So the force of gravity between the two just follows from the law of universal gravitation, g times little m times big M over what distance? D squared, correct? Okay, well that's the force that causes mass m to orbit in its circular path. So mass m is orbiting a circle with a radius of x, while mass little m is orbiting with a circle with a radius of d minus x. So if we set gravitational force equal to centripetal force for either planet, or I'm sorry, either star in this case, we're talking about binary star, not binary planet, then we can say g mm over d squared equals, let's say that gravitational force is the centripetal force for the larger mass. So that's got to equal m v squared over, yeah, you're tempted to say r, but the radius, in that case we've already labeled, that would be x. Okay. Just as well, we could say the gravitational force is providing centripetal force for the smaller mass. And it has a different velocity, v squared, divided by d minus x. Now let me call this velocity 1 and velocity 2. They don't have the same velocity. However, they do go in a circular path. And for a circular path, velocity is equal to 2 pi radius divided by time period. So they don't have the same speed, they don't have the same radii, but they do share the same period. g(m)m over d squared equals capital M times 2 pi x over t quantity squared, all divided by x. g(m)m over d squared equals little m times 2 pi quantity d minus x divided by t, all squared, divided by d minus x. So you can see I'm just equating gravitational force and centripetal force for the larger star, and I'm also doing the same calculation for the smaller of the two stars. So in step 3, we find in both columns that the mass cancels out, and we can also cancel out, well, let's write this out a little more clearly. G times little m over d squared is equal to 4 pi squared x squared over x t squared. So now I can cancel out one of these x's, or I can say g times capital M over d squared is equal to 4 pi squared d minus x quantity squared over d minus x t squared, and I can cancel out one of the d minus x. So period squared is equal to 4 pi squared x d squared divided by g lowercase m. And it's also fair to say period squared is equal to 4 pi squared d minus x times d squared divided by g times large M. But they both rotate, orbit around that center of mass with a common period of orbit. So I can set these two expressions equal to one another. When I do that, the 4 pi squared cancels out, the capital G cancels out, and we're left with an expression that says xd squared over lowercase m equals d minus x times d squared over capital M. Actually, the d squared even cancels out, and now we have capital Mx is equal to lowercase md minus lowercase mx, which leads to an expression that says lowercase m plus capital M quantity times x is equal to lowercase md, and that can be reduced to x equals md over m plus m. Now, do you see what we really just proved? We've just come up with a derivation for the equation for finding the center of mass for any system. See, we can create an origin, an xy axis, and imagine putting the larger of the two stars at the origin. There's our capital M, and there's the smaller of the two stars. Now, the formula we've used in the past for center of mass is we sum up the product of any point particle's mass and its position divided by the total mass of the system. Well, in this case, the product of mass and position for the larger star is 0 because it's sitting at the origin. So the location of the center of mass should be equal to little m times d divided by the total mass, which would be little m plus big M, and you can see these are both the same expression. We can move beyond a study of binary stars and imagine a system of 3 stars orbiting around their common center of mass. So the center of mass has to be located at the geometric center if we assume in this case that all 3 of our stars are of the same mass, which we'll just call m. So if they're all equidistant from one another, we formed a equilateral triangle, and we can say that the distance between the 2 stars is d. So let's see if we can figure out 2 things. 1, what's the speed? And 2, what's the period of orbit? Actually, let's give some numerical values. Let's say that each of these stars has a mass equal to 1 solar mass. In other words, it matches the mass of our local star, the Sun, or Sol. So the Sun has a mass of 1.99 times 10 to the 30th kilograms. And then let's also use a common distance. Let's say that the distance between the stars is the same as the distance between the Earth and the Sun. That distance, the distance between the Earth and the Sun, has a special name to it. It's called an astronomical unit, an AU. And 1 AU is equal to 1.5 times 10 to the 11th meters. Maybe we'll wait until the very end to plug in numerical values. So for now, let's see if we can derive just an algebraic expression that'll predict the velocity of orbit. So these 3 stars are going to move along a circular path. The center of that circular path is the center of mass of the whole system. They all share a common tangential speed. We want to figure out what that's equal to. Well, the reason they're moving in a circle has to be due to a force that points toward the center of the circle. So let's just pick, how about we pick the one at the top there? We'll pick that shaded in of the 3 stars. Okay, so what are the forces acting on it? There's only 2 forces. There's the gravitational pull to the star on the lower left, and there's a gravitational pull from the star on the lower right. The net force from these has to be a net force that points straight down. The horizontal components of these forces I've labeled as F are going to cancel out, and so it's only the components that lie along the y-axis that are going to add up. So we can say there's a net force toward the center, and that net force, if we label this angle as theta, I think we agree that angle would be 30 degrees, correct? Okay, so that net force would be equal to 2, since there's 2 of them, F cosine theta, because we're just finding the components that lie adjacent to the known angle. So the net force is 2F cosine theta, but that net force has to be centripetal in nature, so 2F cosine theta has to be equal to mv squared over r. Okay, well, what's the value of r? Let's see. If we call that r, and this is theta, then this side of a right triangle is d over 2, and I know that cosine theta has to be equal to adjacent over hypotenuse, so cosine theta is d over 2 over r, so r is equal to d divided by 2 cosine theta. Okay, so the net force of 2F cosine theta has to be the centripetal force of mv squared over r. So 2F cosine theta is mv squared over d over 2 cosine theta. But what is this F? Well, if it represents the mutual force of attraction between one of the stars and one other based on the superposition principle, then 2 times g_m divided by d squared cosine theta is equal to, let's multiply top and bottom by 2 cosine theta, is equal to 2 cos theta mv squared over d. So the cosine theta washes out, the 2 disappears, we can cancel out one of the m's and one of the d's, and now we're left with gm over d is equal to v squared. So isn't that interesting? V is the square root of gm over d. That equation looks familiar. What about the period? Period can be found knowing that speed is circumference divided by period. So period is equal to circumference divided by speed. And in this case, it's the same thing as 2 pi r times the inverse of v. So it's 2 pi. And remember what r is equal to. R is d over 2 cosine theta. So 2 pi times d over 2 cosine theta. And then the inverse of v would be the square root of d over gm. So we can cancel out that 2. We can say this is the same thing as the square root of d squared. So the period should be equal to pi over cosine theta times the square root of d cubed over gm. Grab your calculators. Let's do a quick calculation. If we really did have a triple star system where all the stars have one solar mass and they're separated by 1 astronomical unit, then we have some numerical values we can apply to the formulas that we've just derived. The tangential speed for any of these stars would be equal to the square root of 6.67 times 10 to the negative 11th times 1.99 times 10 to the 30th divided by 1.5 times 10 to the positive 11th. This comes out to about 29,747 meters per second. What about the period? Pi divided by cosine of 30 degrees times the square root of 1 astronomical unit cubed, in other words 1.5 times 10 to the 11th cubed, divided by 6.67 times 10 to the negative 11th times the mass of the star. If that really is a solar mass, it's 1.99 times 10 to the 30th. So I find a period of 1.83 times 10 to the 7th. Hard to relate to. Let's divide this by 60. Still a very large number. 3.05 times 10 to the 5th minutes. Let's divide that by 60. 5,081 hours. Still hard to relate to. Let's divide that by 24. 211 days. Oh, now I get a sense of it. It's less than a year. In fact, if I divide that by 365, we get about 58% of a year. Okay, so thanks for tuning in.